Hi, my name is Oktay. Welcome to today's video about the LK-99 superconductor. This is our original picture of Sukbae, Ji-Hoon Kim, and Young-Wan Kwon. Their sample of LK-99 it was discovered in 1999. It has this number 99, and the letters L and K come from the last names of Lee and Kim. This is a lead apatite compound that is doped with copper ions. It is related to hydroxyapatite, which is a mineral in teeth and bones. And this is the formula of LK-99, lead copper phosphate oxide. X is important. It has to be between 0.9 to 1.1, so about 10% replacement of lead with copper. It's a non-stoichiometric compound. Its critical temperature, according to scientists, is above 127 degrees Celsius. It's made of cheap elements. And these three scientists have already applied for a patent for this compound. However, no other scientific group was able to confirm the superconductivity at room temperature at normal pressure of 1 bar that these scientists claim. However, another group has confirmed superconductivity at 100 Kelvin, which is minus 170 degrees. This is the structure of LK-99. It is a modified lead apatite. There are two kinds of lead ions. In black, the outer lead ions. In gray, the inner lead ions. They are separated by the phosphate groups. In the middle, there are the oxide ions. This is a column structure. And the replacement with copper causes a shrinkage of by 0.48%. And another theoretical work suggested that the oxide ions prefer the maximum distance from the copper ions that causes stress. This is a mineral Lanarkite lead sulfate oxide from the South Lanarkshire in Scotland. This is one component for the synthesis of LK-99. This is the synthesis of the LK-99. First step is production of Lanarkite from lead oxide and lead sulfate. Second step is synthesis of copper 1 phosphide from the elements. Third step is the synthesis of LK-99 from Lanarkite plus copper phosphide plus oxygen in a vacuum tube at 925 degrees Celsius. And that gives you LK-99 plus sulfur byproduct. However, there were other two papers that described impurities of copper 1 sulfide in the LK-99 samples. So how can you solve this problem? This is how you do it. You find another way to make LK-99 without sulfur. That's the work of P. Pupal and colleagues from Germany and Indonesia. This is the alternative synthesis from 9 lead oxide plus 1 copper oxide plus 9 ammonium dihydrogen phosphate. This mixture is heated at 750 degrees Celsius for 10 hours. Then it's grinded and heated again for another 10 hours. The product is LK-99. This group made single crystals with the traveling solvent floating zone TSFZ method. This sample was an insulator. There were no superconductivity found, and they could not detect any anomalies for temperatures up to 800 Kelvin. Another work of Changming, Viktor, Christiansson, Philipp, Werner from China and Germany. They made a dynamical mean field theory of LK-99. And this work confirms that lead apatite is an insulator in this picture at the right. This is the Fermi level, this energy that you need to add one more electron to the structure. And they think LK-99 has two copper D bands near the Fermi level and two oxygen P bands below. This is another picture of the structure of LK-99 from another perspective. The outer lead ions are partially replaced by copper ions. And this causes shrinkage and stress, produces quantum wells, and gives LK-99 superconductivity according to Lee, Kim, and Kwon. The oxide ions in the middle have occupy only 1/4 of the available positions. Their position is not relevant for the band structure. However, the stoichiometry of this compound is very important for the band structure. This is a picture of Wannier functions. These are localized molecular orbitals of crystalline systems. At the top, that's nitrogen. At the bottom, that's palladium dinitride. There is a hybridization of copper d and oxygen p orbitals that makes flat copper bands due to the spatial separation of the copper atoms. And LK-99 samples are thought to be heterophases with patches with higher copper concentrations. And it could be that not only the outer but the inner lead ions are replaced by the copper ions. Theoretical work shows that this could be energetically better. This is an example of spin-orbit coupling for the element hydrogen. You can see the 2s and 2p orbitals. Yeah. There's a work of Hua Bai and colleagues from China. This is the relativistic interaction between the magnetic dipole of the electron, its orbital motion, and the electrostatic field of the nucleus. You get a fine structure splitting of the electron levels, and you can even get a hyperfine structure splitting from the electromagnetic multipole interaction between the nucleus and the electron clouds. This original picture of LK-99 sample of Li and Kim. The work of Hua Bai and colleagues from China predict that spin-orbit coupling is relevant to the LK-99 because of the high concentration of lead. Their first principal calculations show that LK-99 is a semiconductor, ground state is ferromagnetic, with a flat conduction band, and they confirm that the copper ions make the phosphate ions groups rotate. This is a picture of a phonon, which is a quantized sound wave. This is very important for superconductivity. Lambda is the wavelength of the sound wave. There's a work of ZhiXiang, colleagues from Germany, USA, and Spain. They made phonon spectra of LK-99, and they think that LK-99 is metastable. The stable compound, according to them, is lead copper phosphate hydroxide. And this group thinks the copper replacement in LK-99 is very low. Their samples were at least three-phase materials. This is the phenomenon of percolation. This is a change to a network when links are added. At the bottom left, you can see P, this is the proportion of bonds among possible links. You can see the change if P increases. In this animation, the connected sites have the same color. There's a work of Qiang and colleagues from China. They propose a current percolation model for LK-99 with lead and copper current channels. These are copper-lead islands with different concentrations that approach each other at low temperatures. But this group could not observe the Meissner-Ochsenfeld effect. There's another work of Ning Chen and colleagues from USA and China. They made quantum mechanics calculation of the electron band structure. And they think that the critical temperature of LK-99 could be higher than cuprates, and that even room temperature superconductivity is possible, theoretically. This is a nice picture of the project Wendelstein 7X from Germany. This is a project for the nuclear fusion. In this picture, you can see the measurement of the coils. The total mass of the machine is more than 750 tons. And this project is a €1 billion project. That was today's video about the LK-99 superconductor and newest scientific papers. Thank you for watching. Have a nice day. Bye-bye.